Good evening, everyone, and welcome to your favorite sleep channel, The Droning Professor. Tonight we're going to learn about quantum entanglement across vast distances. As you make yourselves comfortable, please take a moment to let us know where you're listening from, and feel free to subscribe. Now, as always, take a moment for some deep breaths, letting your mind and body relax for a good night of sleep. So, we're going to talk about one of the strangest, most counterintuitive, and frankly most beautiful phenomena in all of physics, quantum entanglement across vast distances. Now, I know what you're thinking. You're thinking, oh great quantum mechanics, here we go with the math and the confusion and the cat that's both alive and dead. And yes, we will get into some of that, but I promise you this. By the end of tonight, you're going to understand why Albert Einstein called entanglement spooky action at a distance, and why he was so bothered by it that he spent years trying to prove it couldn't be real. Spoiler alert. He was wrong, but he was wrong in the most interesting way possible. Let's start with a question. What is quantum entanglement? At its most basic level, entanglement is a phenomenon where two or more particles become correlated in such a way that the quantum state of one particle cannot be described independently of the others, no matter how far apart they are. I know, that sounds like word salad. Let me try again. Imagine you have two coins. Normal coins, the kind you use to buy coffee or make terrible financial decisions at vending machines. You flip one coin in New York, and I flip the other in Tokyo. The results are independent, right? Your coin has a 50-50 chance of being heads or tails, and so does mine. Nothing you do to your coin affects mine. They're just coins, living their best independent coin lives. Now imagine we have quantum coins. These aren't regular coins. These are weird, quantum mechanical coins that we've prepared in a special way so that they're entangled. You take one to New York, I take one to Tokyo. Before we look at them, each coin exists in what we call a superposition state. It's not heads and it's not tails. It's both, simultaneously, in a very real quantum mechanical sense. And here's where it gets weird. The moment you look at your coin in New York and it turns out to be heads, my coin in Tokyo instantaneously becomes tails. Not because there's some signal traveling between them, but because they're part of a single quantum system. Their fates are linked, entangled, bound together by the strange rules of quantum mechanics. Einstein hated this, absolutely hated it. And to understand why, we need to back up and talk about what was happening in physics in the early 20th century. Because the story of entanglement is really a story about the collapse of everything we thought we knew about reality. Before 1900, physics was in pretty good shape. We had Newton's laws of motion, which explained how objects move. We had Maxwell's equations, which explained electricity and magnetism and light. The universe was deterministic, predictable, clockwork. If you knew the positions and velocities of all particles at one moment, you could, in principle, calculate everything that would ever happen. The French mathematician Pierre-Simon Laplace famously said that such an intellect would have nothing uncertain, and the future, as the past, would be present to its eyes. The universe was a giant, complicated machine, and we were just figuring out how all the gears worked together. Then came quantum mechanics, and everything went absolutely bonkers. It started innocently enough. In 1900, Max Planck was trying to solve a problem about blackbody radiation. The details aren't important, but basically the classical equations gave you nonsense answers. So Planck made a desperate mathematical move. He assumed that energy came in discrete chunks, or quanta. He thought it was just a mathematical trick, not something real. Planck himself said it was an act of desperation. But it worked. The equations matched the experimental data perfectly. Then Einstein, yes, that Einstein, came along in 1905 and said, wait a minute, what if light actually does come in chunks? What if these quanta are real things? He used this idea to explain the photoelectric effect. where light knocks electrons out of metal. This was revolutionary and, frankly, pretty weird. Light is a wave, everyone knew that. We had done the experiments. Thomas Young had demonstrated interference patterns way back in 1804, but Einstein was saying light is also a particle. It's both, somehow. This is wave-particle duality, and it's one of the fundamental weirdnesses of quantum mechanics. Then Niels Bohr showed up and said, okay, if light can act like particles, maybe particles can act like waves. He developed a model of the atom where electrons orbit the nucleus, but only in specific allowed orbits. Electrons could jump between these orbits by absorbing or emitting photons, those chunks of light Einstein talked about. This explained why atoms emit and absorb light at specific wavelengths. It was weird, but it worked. Louis de Broglie took this even further in 1923. He said, if light waves can act like particles, why can't particles act like waves? And he derived an equation showing that every particle has an associated wavelength equal to Planck's constant divided by the particle's momentum. The equation is lambda equals h over p, where lambda is the wavelength, h is Planck's constant, and p is momentum. This sounds insane. You're telling me that a baseball has a wavelength? Yes, but it's incredibly tiny because the baseball has a lot of momentum and Planck's constant is very small. For electrons, though, which have very little momentum, the wavelength is significant. And sure enough, in 1927, Clinton Davison and Lester Germer showed that electrons really do create interference patterns, just like waves. By the late 1920s, physicists had developed the full mathematical framework of quantum mechanics, primarily thanks to Werner Heisenberg, Erwin Schrödinger, and Max Born. Schrödinger developed his famous wave equation, which describes how quantum systems evolve over time. The wave function, usually written with the Greek letter psi, contains all the information about a quantum system. But here's the weird part. The wave function doesn't tell you where a particle is. It tells you the probability of finding the particle at different locations if you look for it. The square of the absolute value of the wave function, psi squared, gives you the probability density. Before you measure, the particle doesn't have a definite position. It exists in a superposition of all possible positions. The act of measurement causes what we call the collapse of the wave function, forcing the particle to choose a definite position. This probabilistic interpretation was primarily due to Max Born, and it drove Einstein absolutely crazy. He famously said, "God does not play dice with the universe." Born later quipped that Einstein should stop telling God what to do. This is one of the great philosophical debates in physics, and it's still not entirely resolved. Heisenberg discovered his uncertainty principle, which says that you can't simultaneously know both the position and momentum of a particle with arbitrary precision. The more precisely you know one, the less precisely you can know the other. Mathematically, the uncertainty in position, which we write as delta x, multiplied by the uncertainty in momentum, delta p, must be greater than or equal to Planck's constant divided by 4 pi. The equation is delta x times delta p is greater than or equal to h bar over 2, where h bar is Planck's constant divided by 2 pi. This isn't just a limitation of our measuring instruments. It's a fundamental property of nature. It's not that the particle has a definite position and momentum and we just can't measure them. The particle literally doesn't have definite values for both simultaneously. Now, all of this is weird enough, but entanglement takes it to another level. The phenomenon was first seriously discussed in a famous paper from 1935 by Einstein, Boris Podolsky, and Nathan Rosen. This paper is known by the initials of its authors, the EPR paper or the EPR paradox. Einstein and his colleagues weren't trying to explain entanglement. They were trying to prove that quantum mechanics was incomplete, that there must be some deeper theory underneath it that would restore determinism and locality to physics. Here's their argument. Take two particles that interact and then fly apart. According to quantum mechanics, until you measure them, each particle exists in a superposition of states. But because they interacted, their wave functions become entangled. If you measure a property of one particle, you instantly know the corresponding property of the other particle, no matter how far apart they are. Einstein argued that this was absurd. How could measuring one particle instantly affect another particle light years away? That would require faster-than-light communication, which violates special relativity, one of Einstein's own theories. Therefore, Einstein concluded the particles must have had definite properties all along. There must be hidden variables that quantum mechanics doesn't account for, variables that determine in advance what the measurement results will be. Quantum mechanics is just incomplete. It doesn't give you the full story. This seemed like a reasonable argument. It's certainly more intuitively satisfying than saying that particles can instantaneously affect each other across arbitrary distances. But here's the thing. Being intuitive doesn't make something true. And in 1964, a physicist named John Stuart Bell figured out how to test whether Einstein was right. Bell derived a mathematical inequality, now called Bell's inequality, that any theory based on local hidden variables must satisfy. Local means that what happens at one location can't instantly affect what happens at another location. Hidden variables means there are predetermined values that we just don't have access to. Bell showed that quantum mechanics predicts violations of this inequality in certain experimental setups. So if you do the experiment and Bell's inequality is violated, then local hidden variables can't exist. Either the universe is non-local, meaning particles can affect each other instantly across distances, or it's not realistic, meaning particles don't have definite properties until you measure them, or both. Any way you slice it, our intuitive understanding of reality has to give. Let me explain Bell's inequality in a bit more detail because it's really quite elegant. Imagine we have two entangled particles flying off in opposite directions toward two detectors. Each detector can be set to measure one of several different properties. For simplicity, let's say each detector has three possible settings, A, B, and C. In a universe with local hidden variables, the particles would leave the source with predetermined results for each possible measurement. Particle 1 would have values for a 1, B1, and C1, and Particle 2 would have values for a 2, B2, and C2, all determined at the moment they were created. Now, if the particles are anti-correlated, meaning when they give opposite results when you measure the same property, then we can set up a mathematical relationship between the probabilities of different measurement outcomes. Bell showed that if local hidden variables exist, then the probability that measurements at settings A and B give different results, plus the probability that measurements at settings B and C give different results, must be greater than or equal to the probability that measurements at settings A and C give different results. This is Bell's inequality. Quantum mechanics predicts something different. For appropriately entangled particles and appropriately chosen measurement angles, quantum mechanics predicts correlations that violate Bell's inequality. The violation is small but detectable. So now we have a testable prediction. Do the experiment. If you see violations of Bell's inequality, Einstein's local hidden variables don't exist. Quantum mechanics, with all its weirdness, is right. The first experimental test was done by John Clauser and Stuart Friedman in 1972. They used entangled photons, particles of light, and they found violations of Bell's inequality, supporting quantum mechanics. But there were loopholes. Maybe the detectors weren't efficient enough. Maybe some signal passed between them. Over the following decades, experimenters worked to close these loopholes, doing more and more careful experiments. Alain Aspect did landmark experiments in the early 1980s using faster switching and better detection. John Clauser, Alain Aspect, and Anton Zeilinger won the Nobel Prize in Physics in 2022 for their work on entanglement and Bell's inequalities. The experiments kept getting better. In 2015, Three separate groups performed loophole-free Bell tests. They used entangled photons and fast switching and detectors placed far enough apart that no signal traveling at the speed of light could pass between them during the measurement. All three experiments showed violations of Bell's inequality. The verdict is in. Einstein was wrong. Entanglement is real. The universe is non-local in a very specific quantum mechanical sense. Now, let me be very clear about what non-locality means here, because this is a common source of confusion. When we say entanglement is non-local, we don't mean you can use it to send information faster than light. You can't. Here's why. When you measure your entangled particle, you get a random result. Completely random. It might be spin up or spin down, or whatever property you're measuring. You have no control over what you get. Now, because the particles are entangled, when I measure my particle, I'll get a correlated result. If you got spin up along a certain axis, I'll get spin down along that same axis, or vice versa, depending on how the particles were prepared. But here's the critical point. I don't know what result you got unless you tell me through some classical communication channel, like a phone call, or an email, or a message tied to the leg of a particularly speedy pigeon. From my perspective, I just see a random sequence of spin-ups and spin-downs. It's only when we compare our results later that we see the correlations. The entanglement gives us correlations, but those correlations don't let us send information faster than light. No usable information travels instantly. The weirdness is that the correlations exist, not that we can exploit them for communication. This is sometimes called the no-signaling theorem, and it's why entanglement doesn't violate causality or special relativity in the way that faster-than-light communication would. So, what is entanglement really? What's actually happening? Well, that depends on which interpretation of quantum mechanics you prefer, and there are many. The most common interpretation, taught in most textbooks, is the Copenhagen interpretation, developed primarily by Niels Bohr and Werner Heisenberg in the 1920s. According to this view, the wave function contains all the information about a system, but that information is fundamentally probabilistic. Before measurement, particles don't have definite properties. They exist in superpositions. Measurement causes the wave function to collapse, forcing the system to take on definite values. For entangled particles, they share a single wave function. Measuring one particle collapses the entire shared wave function, which is why the other particle's state becomes determined instantly. The Copenhagen interpretation doesn't really explain how or why collapse happens. It just says that it does, and we should stop asking philosophical questions and focus on calculating predictions, which the theory does magnificently well. Einstein hated the Copenhagen interpretation. He wanted a complete, deterministic theory. He wanted particles to have definite properties, whether or not we measure them. As I mentioned, he thought there must be hidden variables. But Bell's theorem and subsequent experiments seem to rule that out, at least for local hidden variable theories. There are other interpretations. The many worlds interpretation, proposed by Hugh Everett in 1957, says that wave function collapse never actually happens. Instead, every time a quantum measurement occurs, the universe splits into multiple branches. In one branch, you measure spin up. In another branch, you measure spin down. Both outcomes happen, just in different, non-interacting parallel universes. This sounds like science fiction, but it's a legitimate interpretation taken seriously by many physicists. In the many worlds view, entanglement doesn't involve instantaneous effects across distance. Rather, the measurement results become correlated through the branching structure of the multiverse. Your branch and my branch become linked through the entanglement. Then there's the de Broglie-Bohm interpretation, also called pilot wave theory, which says particles do have definite positions at all times, guided by a wave. This interpretation manages to be deterministic and reproduce all the predictions of quantum mechanics, but the wave is non-local. It guides particles instantly across arbitrary distances. So you get your determinism back, but you have to accept non-locality explicitly built into the theory. There's also quantum Bayesianism, or cubism, which treats the wave function as representing an observer's subjective knowledge about a system rather than an objective feature of reality. And there are others: spontaneous collapse theories, consistent histories, relational quantum mechanics. The list goes on. The dirty secret of quantum mechanics is that, after more than 90 years, we still don't agree on what it all means. The math works spectacularly well. The predictions are confirmed to ridiculous precision. But the interpretation, the question of what's really happening, remains hotly debated. My personal view, for what it's worth, is that we should take quantum mechanics seriously as a description of reality, weirdness, and all. Entanglement tells us something profound about the nature of space and the interconnectedness of the universe. But I also think we're probably missing something, some deeper principle that will make it all make sense. Or maybe not. Maybe the universe really is just this weird, and we need to update our intuitions. Nature doesn't care what we find intuitive. Let's talk about some specific examples of entanglement and how we create entangled states in practice. The most common method involves something called spontaneous parametric down conversion. You take a special nonlinear crystal, something like beta barium borate or potassium titanyl phosphate, and you shine an ultraviolet laser into it. Occasionally, a single photon from the laser will split into two lower energy photons. Because of conservation of energy and momentum, these two photons are correlated. They're entangled. If one photon has vertical polarization, the other has horizontal polarization. If one has spin up, the other has spin down. These photon pairs can then be sent off in different directions to distant detectors. Another common system uses atoms. You can trap atoms with lasers and magnetic fields, cool them down to nearly absolute zero, and manipulate their quantum states with precisely timed laser pulses. By carefully controlling the interactions between atoms, you can create entangled states of multiple atoms. Ion traps are particularly good for this. You trap electrically charged atoms, ions, in electromagnetic fields, and use lasers to manipulate their internal energy states and their motion. Groups led by researchers like David Wineland and Rainer Blatt have created entangled states of dozens of ions. Superconducting circuits are another platform. These are tiny electrical circuits made from superconducting materials that conduct electricity without resistance at very low temperatures. They act as artificial atoms, with discrete energy levels that you can manipulate. Groups at places like Google and IBM and Yale have built quantum processors with superconducting qubits that can be entangled and manipulated to perform quantum computations. Now let's talk about entanglement across truly vast distances, because that's what makes this so mind-blowing. In the lab, you might have entangled particles separated by a few meters or tens of meters. But there's no fundamental limit to how far apart entangled particles can be. The correlations persist regardless of distance. This has been tested experimentally over larger and larger distances. In 2007, a group led by Anton Zeilinger established entanglement between two particles separated by 144 kilometers across the Canary Islands. They created entangled photon pairs in one location, sent one photon to the island of La Palma and the other to Tenerife, and demonstrated that the photons were still entangled despite the distance. In 2017, China launched the Messias satellite, named after an ancient Chinese philosopher. This satellite is designed specifically to test quantum communication and entanglement over unprecedented distances. Researchers led by Zhen Weipan used Messias to create entangled photon pairs in space and beam them down to ground stations in China, separated by over 1,200 kilometers. They then performed measurements demonstrating that the photons remained entangled despite traveling hundreds of kilometers through the atmosphere and being separated by over 1,000 kilometers. This is the longest distance over which entanglement has been demonstrated. The correlations predicted by quantum mechanics held perfectly, even with entangled particles separated by more than the width of Texas and Louisiana combined, if you're thinking in American geography. Why is this important? Well, beyond just being a stunning demonstration of quantum mechanics, entanglement has practical applications. The most mature is quantum cryptography, specifically quantum key distribution. Here's the idea. Suppose you want to send a secret message. You encrypt it with a key, a random string of bits. As long as the key is truly random, used only once, and kept secret, the encryption is unbreakable. This is called a one-time pad, and it's been known since the early 20th century. The problem is distributing the key. If you meet in person, great, but that's not always practical. If you send the key electronically, someone might intercept it. Quantum key distribution solves this problem using entanglement or related quantum phenomena. Here's one protocol called E91 after the physicists Arthur Eckert, who proposed it in 1991. You create entangled photon pairs. Send one photon to Alice, the other to Bob. Alice and Bob each measure their photons along randomly chosen directions. They then publicly announce their measurement directions, but not their results. For measurements along the same direction, their results will be correlated because of the entanglement. They can use these correlated results to generate a shared random key. Here's the clever part. If an eavesdropper, traditionally called Eve, tries to intercept the photons and measure them, she'll disturb the quantum state. Entanglement is fragile. Any measurement or interaction with the environment can destroy it. Alice and Bob can detect this disturbance by comparing a subset of their measurements. If the correlations match what quantum mechanics predicts for perfect entanglement, they know no one intercepted the photons. If the correlations are weaker, someone was listening in, and they discard that key and try again. The laws of quantum mechanics guarantee the security. You can't eavesdrop without being detected. Quantum key distribution systems have been built and deployed commercially. There are quantum networks in China, Europe, and the United States. The distances are limited by photon loss in optical fibers or the atmosphere, typically to a few hundred kilometers, but satellites like Messius extend this to intercontinental distances. In 2017, China used Messius to establish a quantum encrypted video call between Beijing and Vienna, the first intercontinental quantum communication. Entanglement is also the basis for quantum computing, one of the most exciting and hyped areas of modern technology. A classical computer stores information in bits, each of which is either 0 or 1. A quantum computer uses quantum bits, or qubits, which can be in a superposition of 0 and 1 simultaneously. Because of superposition and entanglement, a quantum computer with n qubits can be in a superposition of 2 to the power of n different states simultaneously. This allows quantum computers to explore many possible solutions to a problem in parallel. Certain problems are believed to be much faster on a quantum computer than any classical computer. Peter Shor showed in 1994 that a quantum computer could factor large numbers exponentially faster than the best-known classical algorithms. This is important because much of modern cryptography relies on the difficulty of factoring large numbers. If large quantum computers are built, they'll break current encryption methods. Love Grover showed in 1996 that quantum computers can search unsorted databases quadratically faster than classical computers. Building a quantum computer is incredibly difficult. Qubits are fragile. They interact with their environment, causing decoherence, where the quantum information is lost. You need to isolate them extremely well and perform operations faster than decoherence occurs. You also need many qubits. Current quantum computers have tens to hundreds of qubits, but useful applications may require thousands or millions. Companies like IBM, Google, and Rigetti, and research groups around the world are racing to build better quantum computers. In 2019, Google announced that their Sycamore processor achieved quantum supremacy, performing a specific calculation faster than any classical computer could. The task was admittedly contrived, designed to be hard for classical computers, and didn't solve any useful problem. IBM disputed the claim, arguing that a classical computer could solve the same problem in a reasonable time with clever algorithms. The debate continues, but we're clearly making progress. Entanglement also enables quantum teleportation. Now, before you get too excited, this isn't teleportation in the Star Trek sense. You can't beam yourself to Mars. But you can transfer the quantum state of a particle from one location to another without the particle itself traveling there. Here's how it works. Start with two entangled particles. Give one to Alice, one to Bob. Alice also has a third particle whose quantum state she wants to send to Bob. Alice performs a special joint measurement on her entangled particle and the particle she wants to teleport. This measurement entangles all three particles in a particular way and gives Alice 2 bits of classical information. She sends these 2 bits to Bob through a classical channel. Bob then performs an operation on his entangled particle, conditioned on the 2 bits he received. After this operation, Bob's particle is in the same quantum state that Alice's original particle was in. The original particle state is destroyed in Alice's measurement. You can't clone quantum states. That's another rule of quantum mechanics. But the state has been teleported to Bob. This was first demonstrated experimentally in 1997 by Anton Zeilinger's group with photons. Since then, quantum states have been teleported over longer distances and with different types of particles. In 2012, Zeilinger's group teleported quantum states across the Danube River in Vienna, a distance of 143 kilometers. In 2017, using the Messias satellite, Chinese researchers achieved quantum teleportation from the ground to the satellite over a distance of around 1,400 kilometers, setting another distance record. Why is this useful? For quantum communication networks. If you want to send quantum information from one quantum computer to another over long distances, quantum teleportation is one way to do it. It's also used in certain quantum error correction schemes, which are essential for building reliable quantum computers. Speaking of error correction, let's talk about that for a moment because it's fascinating. Classical computers use error correction all the time. Your hard drive has extra bits that allow it to detect and correct errors caused by cosmic rays or manufacturing defects. The idea is redundancy. Store each bit multiple times. If one copy gets flipped, you can take a majority vote to recover the correct value. For quantum computers, it's much harder. You can't just copy a qubit. The no-cloning theorem, proved by William Wouters and Wojciech Zurek in 1982, says you can't make an exact copy of an unknown quantum state. So how do you protect quantum information from errors? The answer, discovered by Peter Shor in 1995 and independently by Andrew Steen in 1996, is quantum error correction codes. You encode the information of one logical qubit into multiple physical qubits in a clever entangled state. Errors on individual physical qubits can then be detected and corrected without ever measuring, and thus destroying, the logical qubit's quantum state. It's a beautiful application of entanglement, and one of the reasons large-scale quantum computers might actually be possible. Entanglement also has implications for our understanding of space-time. This is more speculative, but there's growing evidence that entanglement and the geometry of space-time are deeply connected. The idea comes from studying black holes. In the 1970s, Stephen Hawking showed that black holes aren't completely black. They emit radiation due to quantum effects near the event horizon, the boundary of the black hole. This Hawking radiation is thermal, like the radiation from a hot object. Hawking calculated the temperature of this radiation. For a black hole of mass m, the temperature is proportional to h bar c cubed divided by 8 pi gm k sub b, where h bar is the reduced Planck constant, c is the speed of light, G is Newton's gravitational constant, m is the mass, and K sub b is Boltzmann's constant. For stellar mass black holes, this temperature is incredibly tiny, much colder than the cosmic microwave background, so they're actually absorbing more radiation than they emit. But for smaller black holes, the temperature is higher. The fact that black holes have a temperature means they have entropy, a measure of disorder or the number of possible microstates. Jacob Bekenstein and Hawking showed that the entropy of a black hole is proportional to the area of its event horizon, not its volume. Specifically, the entropy is K sub b times the area divided by 4 times the Planck length squared. The Planck length is the square root of h bar g divided by c cubed, about 10 to the power of minus 35 meters. This is incredibly small. This result is weird. For ordinary objects, entropy is proportional to volume because it's related to the number of particles and their possible configurations. For a black hole, it's proportional to area. This suggests that the information about what's inside a black hole is somehow encoded on its surface. This is the holographic principle, and it has led to deep insights into quantum gravity. Here's where entanglement comes in. In 2006, Shinsei Ryu and Tadashi Takayanagi, studying a particular model of quantum gravity called anti de Sitter, conformal field theory correspondence, or ADS CFT for short, found a formula for calculating the entropy of a region in terms of the geometry of spacetime. The entropy is proportional to the area of a certain surface in the higher dimensional spacetime, and this entropy is exactly the entanglement entropy, a measure of how entangled that region is with the rest of the universe. This led physicists like Mark van Ramsdonk and others to propose that spacetime itself might emerge from entanglement. The geometry of space, the fact that there's a notion of distance and locality, might arise from the pattern of entanglement in some more fundamental quantum system. In this view, entanglement isn't just a feature of quantum mechanics, it's the glue that holds space together. If you remove the entanglement, space-time falls apart. This is a radical idea and still very speculative, but it's being actively researched. We might be on the verge of understanding space and time in a completely new way, and entanglement is at the heart of it. Let me tell you about one more experiment because it beautifully illustrates the weirdness of entanglement. It's called delayed choice entanglement swapping, and it was performed by Xiaosong Ma and colleagues in Anton Zeilinger's group in 2012. The setup is complicated, so bear with me. You create 2 pairs of entangled photons. Call them photons 1 and 2 from the first pair, and photons 3 and 4 from the second pair. Photon 1 goes to Alice, photon 4 goes to Bob, and photons 2 and 3 go to a measuring station. Now, photons 1 and 4 were never directly entangled. They came from different pairs. But here's the trick. At the measuring station, you can perform a measurement on photons 2 and 3 that projects them into an entangled state. If you do this, then photons 1 and 4 become entangled even though they never interacted. This is called entanglement swapping. Here's the mind-blowing part. Alice and Bob receive photons 1 and 4 and measure them before the measurement on photons 2 and 3 is performed. So according to the usual forward-in-time view, photons 1 and 4 aren't entangled when Alice and Bob measure them. But if you later perform the entangling measurement on photons 2 and 3, and then look at the correlations between Alice's and Bob's results, you find that they're entangled. It's as if the later measurement on photons 2 and 3 retroactively entangled photons 1 and 4, even though those measurements already happened. This doesn't violate causality because, again, Alice and Bob see only random results individually. It's only when they compare their data after learning the results of the measurement on photons 2 and 3 that they see the correlations. No information travels backward in time. But it does show how slippery our usual notions of past, present, and future become in the quantum world. The order of events becomes ambiguous in a way that classical physics never allowed. So, where does all this leave us? What should we take away from entanglement? First, The universe is deeply, profoundly weird. Our intuitions, evolved to deal with everyday objects moving at everyday speeds, are not reliable guides to the quantum world. Particles don't have definite properties until measured. They can be in multiple states simultaneously, and they can be correlated in ways that defy classical explanation, remaining connected across arbitrary distances. Second, nature is non-local in a specific quantum sense. Measuring one particle can instantaneously determine the state of another, distant particle. This doesn't allow faster-than-light communication, so it doesn't violate special relativity, but it does mean that the universe is more interconnected than we naively thought. Einstein's hope for a local, deterministic hidden variable theory is ruled out by Bell's theorem and experiments. Third, entanglement is not just a curiosity. It's a resource, something we can use to do things that would be impossible classically. Quantum cryptography, quantum computing, quantum teleportation, these are all real technologies in various stages of development that exploit entanglement. We're learning to harness the weirdness of quantum mechanics for practical purposes. Fourth, entanglement might be telling us something deep about the nature of space and time. The holographic principle, the connection between entanglement and space-time geometry, these are hints that our current understanding of physics is incomplete. We don't yet have a complete theory of quantum gravity, a theory that unifies quantum mechanics and general relativity. When we do, entanglement will almost certainly play a central role. Finally, and perhaps most importantly, entanglement reminds us of the power and beauty of science. In the early 20th century, physicists were confronted with experimental results that made no sense. Atoms emitted light at specific frequencies. The photoelectric effect had strange properties. Classical physics couldn't explain them. Rather than giving up, physicists developed a new theory, quantum mechanics. This theory made bizarre predictions that clashed with our intuitions and with the worldview of the greatest physicist of the age, Albert Einstein. But the predictions were testable. Experiments were done. And quantum mechanics was right. Again and again. Over nearly a century. In every test we've devised, quantum mechanics has passed with flying colors. The universe is weirder than we thought, and that's wonderful. I want to emphasize that we don't have all the answers. The measurement problem, the question of what the wave function really is and what causes it to collapse, remains unresolved. The interpretation of quantum mechanics is still debated. We don't know how to reconcile quantum mechanics with general relativity at a fundamental level. Entanglement raises as many questions as it answers. How does it work? Is there some deeper explanation? Or is entanglement simply a brute fact about the universe? We don't know. And that's okay. That's exciting. It means there's more to discover. If you take one thing away from tonight, let it be this. Entanglement shows us that reality is far stranger and more interconnected than our everyday experience suggests. Two particles, separated by vast distances, can remain correlated in ways that have no classical explanation. This isn't magic or mysticism. It's physics, tested and confirmed by rigorous experiments. And it's a testament to human curiosity and ingenuity that we've been able to discover and understand, at least mathematically, such a counterintuitive phenomenon. Let me spend our remaining time talking about some of the ongoing research and future directions in entanglement science, because this field is very much alive and active. One exciting area is the development of quantum networks. Just as the classical internet connects computers around the world, a quantum internet would connect quantum computers and quantum sensors, allowing them to share quantum information. This would enable distributed quantum computing, where multiple quantum processors work together on a problem. It would allow quantum sensors in different locations to be entangled, improving their precision beyond what's possible with classical coordination. And it would provide unconditionally secure communication through quantum key distribution. Building a quantum internet is challenging. Photons are great for transmitting quantum information because they travel fast and interact weakly with their environment. But they're also easily lost. Send a photon through an optical fiber, and it has maybe a 50% chance of making it 100 kilometers before being absorbed or scattered. For longer distances, you need quantum repeaters, devices that can extend entanglement over longer distances by creating entanglement in stages and then using entanglement swapping to link the stages together. This requires quantum memories, devices that can store quantum states reliably. We're making progress, but practical quantum repeaters are still years away. Satellites offer an alternative. The Messias satellite showed that it's possible to distribute entanglement through space, where photons can travel long distances without being absorbed. Several countries are now working on quantum satellite networks. The European Space Agency has plans for quantum communication satellites. The United States has various programs. There's talk of a quantum internet spanning the globe within the next couple of decades. Another active area is the study of many-body entanglement, entanglement in systems with many particles. In the simple examples I've discussed, we have two entangled particles. But you can have entanglement among 3, 4, a dozen, thousands, millions of particles. The patterns of entanglement in many-body systems are incredibly rich and complex. They're related to phases of matter, transitions between different phases, and the emergence of collective phenomena. For example, topological phases of matter are states where the entanglement pattern has a special structure that makes the system robust against local disturbances. These phases are being studied both for fundamental physics reasons and because they might be useful for building more stable qubits for quantum computing. The idea is that if you encode quantum information in the global entanglement pattern rather than in individual particles, local noise won't destroy the information. This is called topological quantum computing, and it's one approach to building large-scale quantum computers. Entanglement is also being used to study condensed matter physics. When you cool certain materials to very low temperatures, the atoms or electrons can form highly entangled states with exotic properties. Superconductors, where electricity flows without resistance, involve entangled pairs of electrons called Cooper pairs. High-temperature superconductors, discovered in 1986 and still not fully understood, likely involve complex patterns of entanglement. Quantum spin liquids are phases where the magnetic moments of atoms remain highly entangled and fluctuating even at absolute zero. Understanding these systems requires understanding their entanglement structure. There's also growing interest in entanglement in biological systems. Now, I should be careful here. There's a lot of hype and frankly pseudoscience around quantum biology. Just because something is weird or unexplained doesn't mean quantum mechanics is involved. But there are a few legitimate examples where quantum effects, possibly including entanglement, play a role in biology. One is photosynthesis. Plants and bacteria absorb light and convert it to chemical energy with remarkably high efficiency. In 2007, Graham Fleming and colleagues discovered evidence for quantum coherence in the light-harvesting complexes of photosynthetic bacteria. Energy absorbed by chlorophyll molecules seems to exist in a superposition of states, exploring multiple pathways simultaneously to find the most efficient route to the reaction center. Whether this involves entanglement between molecules is still debated, but quantum effects are definitely present and seem to be functional, not just incidental. Another example is in bird navigation. Some birds can sense the Earth's magnetic field and use it for navigation. One proposed mechanism involves a chemical reaction in the bird's eye where two radicals, molecules with unpaired electrons, are created in an entangled state. The magnetic field affects the reaction rate depending on the orientation, and the bird's brain can somehow sense this. This is called the radical pair mechanism, and there's good evidence for it, though the details are still being worked out. Are there quantum effects in the brain, in consciousness itself? This is much more speculative. Roger Penrose and Stuart Hameroff have proposed that quantum processes in structures called microtubules inside neurons are essential for consciousness. Most neuroscientists are highly skeptical. The brain is warm and wet, seemingly the worst environment for maintaining quantum coherence. But the question remains open. We don't understand consciousness, and we don't fully understand the boundary between quantum and classical behavior in complex systems. So maybe there's something there, or maybe not. Time and research will tell. Let me also mention some of the philosophical implications of entanglement beyond what I've already discussed. Entanglement challenges our notions of individuality and separability. In classical physics, objects are distinct. You can talk about this particle and that particle as separate entities with their own properties. But entangled particles aren't fully separate. They're part of a single quantum system. You can't describe one without reference to the other. The whole is not just the sum of the parts. The entangled system has properties that can't be reduced to properties of the individual particles. This has led some philosophers to argue for a kind of quantum holism, where the fundamental entities are not particles but systems, and relationships are as fundamental as the relata. Others have explored connections between quantum mechanics and Eastern philosophies, particularly Buddhism, which emphasizes interconnectedness. Now, I'm cautious about these comparisons. It's easy to read too much into poetic or metaphorical language. But there's no denying that quantum mechanics challenges our Western philosophical tradition, rooted in Democritus and Descartes, that takes individual objects as fundamental. Entanglement also relates to the old philosophical question of determinism versus free will. If the universe is fundamentally probabilistic, as quantum mechanics suggests, then perhaps there's room for free will. Of course, randomness isn't the same as free will. Just because my decisions are random doesn't mean they're free in any meaningful sense. But at least quantum mechanics breaks the deterministic clockwork universe of classical physics. Whether this actually bears on free will is a question I'll leave to philosophers. There's also the question of reality and observation. Some interpretations of quantum mechanics give a special role to observation or measurement. The wave function collapses when measured. But what counts as a measurement? Does it require a conscious observer? Most physicists say no. A measurement is any interaction that causes decoherence, the loss of quantum coherence due to interaction with the environment. This happens constantly, regardless of whether anyone's watching. But the question remains philosophically interesting. What is the status of the wave function before measurement? Is it real, or just a mathematical tool? Different interpretations give different answers. Personally, I find these questions fascinating but also somewhat frustrating. We have a theory that works incredibly well. Quantum mechanics makes predictions, and those predictions are confirmed by experiments. The math is clear, but the interpretation, what it all means, remains murky. Maybe that's okay. Maybe the universe doesn't owe us an intuitive explanation. Or maybe we're missing something fundamental, and future generations will look back at our confusion with amusement. Either way, it's a privilege to live in a time when we can ask these questions and have serious scientific and philosophical discussions about them. Before I close, I want to address a question I sometimes get asked. Could we be living in a simulation, and does quantum mechanics tell us anything about that? The idea is that if we're in a computer simulation, the simulators might use tricks to save computational resources. Maybe the universe doesn't compute the state of a particle until someone looks at it, just like a video game doesn't render the parts of the world you're not looking at. Could wave function collapse be evidence of this? It's a fun idea, but I'm skeptical. First, quantum mechanics doesn't quite work like that. Particles don't have definite states before measurement, but that doesn't mean the wave function isn't being computed. The wave function evolves according to Schrödinger's equation, which is computationally intensive. Second, if we're in a simulation, the simulators could be doing anything. They could be simulating classical physics with quantum mechanics as an emergent phenomenon, or they could be simulating quantum mechanics directly, or something else entirely. Without more information, the simulation hypothesis doesn't really predict or explain anything. It's not testable in any meaningful way. So, while it's entertaining to think about, I don't think it's a scientifically useful idea. What I do think is scientifically useful is continuing to push the boundaries of entanglement research. We should continue to test quantum mechanics in new regimes. Larger objects, longer distances, more complex systems. Every test so far has confirmed quantum mechanics, but maybe at some scale or in some regime, the theory will break down and we'll discover new physics. We should continue to develop quantum technologies. The potential applications of quantum computing, quantum sensing, and quantum communication are enormous, and we should continue to think deeply about what quantum mechanics means, what it tells us about reality. Even if we don't reach definitive answers, the process of asking and exploring these questions is valuable. Science is sometimes portrayed as giving us certainty, final answers to our questions, but that's not really how it works. Science is provisional, always open to revision in light of new evidence. What science gives us is the best understanding we can achieve at any given time, along with the tools and methods to improve that understanding. Quantum mechanics and entanglement are perfect examples. We have a theory that works extraordinarily well, but we also have deep questions about what it means. This isn't a failure of science. It's science working as it should, pushing at the boundaries of knowledge, comfortable with uncertainty and ambiguity while still making progress. I'll leave you with one final thought. When Einstein called entanglement spooky action at a distance, he meant it as a criticism. He thought it showed that quantum mechanics was incomplete, that something was missing. But Einstein was wrong about entanglement. It's real. And yet, in a deeper sense, maybe Einstein was right to be spooked. Entanglement is spooky. It reveals that the universe is fundamentally different from what our intuitions suggest. Reality is non-local, interconnected, probabilistic, and deeply strange. And that's wonderful. That's what makes physics exciting. We live in a universe that constantly surprises us, that resists our attempts to fit it into comfortable boxes, that demands that we question our assumptions and expand our thinking. Quantum entanglement is one of the great discoveries of human civilization. It's a window into the underlying structure of reality. It's a resource we're learning to harness for new technologies. And it's a source of endless fascination and wonder. The fact that two particles separated by thousands of kilometers can remain intimately connected, that measuring one instantaneously affects the other, that this is not only possible but has been demonstrated experimentally beyond any reasonable doubt, should fill us with awe. We live in a quantum universe, and entanglement is one of its most beautiful and mysterious features. The journey of understanding entanglement has taken us from Einstein's skepticism in 1935, through Bell's theorem in 1964, to loophole-free tests in 2015, to satellite-based entanglement distribution in 2017, and to ongoing work on quantum networks and quantum computing today. It's been a journey of nearly 90 years, involving thousands of physicists and countless experiments. And we're still just beginning. The next decades will surely bring new discoveries, new applications, and new puzzles. I hope tonight's discussion has given you a sense of what entanglement is, why it's weird, and why it matters. I hope you've seen that quantum mechanics, for all its strangeness, is a real, tested, reliable theory of nature. And I hope you've gotten a glimpse of the scientific process in action, the interplay between theory and experiment, the importance of precise mathematical predictions, the willingness to challenge even the most brilliant minds, like Einstein, when the evidence demands it. If you're interested in learning more, there are many excellent books on quantum mechanics and entanglement written for general audiences. Brian Greene's The Fabric of the Cosmos, has good chapters on quantum mechanics. Jim Al-Khalili's Quantum, a guide for the perplexed, is accessible and clear. Louisa Gilder's The Age of Entanglement tells the history through the stories of the scientists involved. And if you're feeling more ambitious, there are textbooks. David Griffith's Introduction to Quantum Mechanics is a standard undergraduate text. Nielsen and Chuang's Quantum Computation and Quantum Information is the Bible of quantum information theory. The field is moving fast. New results are published constantly. If you want to keep up, websites like Quantum Magazine and Physics World have excellent articles on recent developments. The RxIve, a preprint server, has all the latest research papers, though they're quite technical. And of course, you can always take more classes, attend seminars, and talk to researchers. The quantum physics community is generally welcoming and happy to share our excitement about this weird and wonderful field. Thank you for your attention tonight. Thank you for staying with me through this journey into the quantum realm. I know it's not easy material. Quantum mechanics is hard. It's counterintuitive. It challenges everything we think we know about reality. But I hope I've conveyed not just the weirdness, but also the beauty and the power of these ideas. Entanglement is real. It's been tested. It works. And it's changing our understanding of the universe and our ability to build new technologies. We live in exciting times, at the frontier of knowledge, pushing at the boundaries of what's possible. Keep asking questions, keep being curious, keep demanding evidence and rigorous thinking, and most importantly, keep your sense of wonder. The universe is an amazing place, stranger and more beautiful than we ever imagined. Good night. And in case you've enjoyed our evening talk so much and still might be awake, here is another educational video for you.